Hello and welcome. So in this video we're going to interpret the regression coefficient estimate results of a log level regression. So suppose that we have the following model that we wish to interpret the results of. So we have wages here is our dependent variable or our response variable, and now it's a function of beta naught, our intercept, plus our beta 1 times log education, plus beta 2 times log experience, plus beta 3 times log age. So in this model, the independent or explanatory variables are education, experience, and age, all in log terms. And then the response variable, wages, are in level terms. And then wages here just are interpreted as monthly earnings. Now let's say that that we've gathered some data and we ran the regression, and suppose that we get the following regression results. So first off, these are completely made up, so don't really take them as any sort of source to get some intuition about how education, experience, and age affect wage. They're completely made up by me. But let's say we get these results. So this is what a typical R output for running a regression and doing a summary looks like. It's a portion of it. So you have our intercept here, which stands in for our beta naught. That's our estimate of beta naught. This 5,000 estimate. Our estimate under education is our estimate for beta 1 here, so 4,025. Our estimate for beta 2 is the experience estimate here. And then the estimate for beta 3, standing in for age, is this 2,350. So how do we interpret that? So let's focus on beta 1. How exactly do we interpret this when it was log education here? So how for example, do we interpret this beta 1 of 4,025? Well, before we could start interpreting results, we need to kind of cover a couple things first. So first off, we need to think about the Gauss-Markov assumptions. So first off, they just kind of need to hold. There is some room for flexibility with the Gauss-Markov assumptions, but let's assume that they hold. Second off, we need our regression coefficient estimates to be statistically significant and practically significant. In terms of statistical significance, we see from our regression results here that we have fairly high t-values and our p-values are near 0, so we could be confident that they're statistically significant. In terms of practical significance, well, practical significance is pretty qualitative, so it's basically is the effect size noticeably big. So given an underlying variation in the variable that we're concerned with, so like say education here, is the coefficient estimate large enough to have like an effect that we'll notice in the real world? Just as an example of practical significance, suppose that you've got an estimate that proves to be statistically significant, but the coefficient is just minuscule, so minuscule that you wouldn't really notice the effect of that in the real world. Then that's practically significant. So let's say that these are both statistically significant and practically significant. And then also when we interpret our beta 1 there, we're assuming that the other independent variables, so experience and age, are held constant. Okay, so with that little notice, let's interpret beta 1. To correctly do this, we need to, let's take the derivative of our model with respect to education. So that's what we're doing here. You can see we have the first derivative of wage with respect to education, or of respect to our total model. So when we take the first derivative, what do we get? Well, we get d wage, the change in wage, is equal to, remember when you take the derivative of a log, you get the partial of that, and then it has a 1 over times whatever that variable was. So if it's like, let's say you had log x and you take the derivative of log x, that's going to be dx over x. So we get this term here when we take the derivative of log education, and then beta 1's in front, so it's times beta 1. So d education here, that's the change in education, and this d wage here, that's the change in wages. So d education over education, that's the change in education in percent. So what's interesting about the change in education in percent is that if you times this by 100, that'll give us, so that's d education divided by education times 100. That'll give us the percent change in education. And the percent change in education is a useful statistic that we could kind of get an intuition from. So let's times both sides by 100 and see what we get. So timesing both sides by 100, we now have 100 times the change in wage. So 100 times D wage is equal to 100 times this change in education in percent times beta 1. So rewriting this, like reinterpreting it just a little bit, remember 100 times the change in education divided by education, that's the percent change in education. So reinterpreting this a little bit, we get 100 times the change in wage is equal to the percent change in education times beta 1. And final step, so what we're saying is that the change in wage here, so D wage, the change in wage, is equal to the percent change in education times beta 1 divided by 100. So let's do that with an example pulled from, with our education example. Our estimate for beta 1 here is 4,025. It's statistically significant. We're going to say it's practically significant. We're going to say that the Gauss-Markov assumptions hold, and holding all the other variables constant. What does this mean, 4,025? So what it means is that if we were to increase education by 1%, then we would expect monthly wages to increase by beta divided by 100, which is 4,025 divided by 100, which is $40.25. So if education is increased by 1%, we expect monthly wages to increase by $40.25. So therefore, another way to say this is holding age and experience constant. A 1% increase in education is associated with a $40.25 increase in monthly wages. That's how you interpret it. Hopefully this was helpful. If it was helpful, be sure to thumb it up, give it a thumbs up, and thanks and have a good day. Bye.